So in this video, we're going to maximize an angle by using the derivative of the arc cotangent function. So this problem says that a photographer is taking a picture of a painting. The painting is hung on a wall. The height of the painting itself is 4 feet, and the camera lens is 1 foot below the lower edge of the painting. How far should the camera be from the painting to maximize the angle subtended by the lenses? So this is a maximization problem. So we know when we're working with a maximization problem that we need a formula that describes the situation, and then we need to take the derivative of that formula. And to find the maximum, we need to determine when is the derivative equal to 0 to get the critical numbers, and when can the derivative be undefined, which will also generate critical numbers for us. So the first thing is going to be to draw a picture that models the problem. So you have a 4 foot high picture. And then a foot lower than that, there's a camera lens. And the camera lens is going to be some distance from the wall on which the picture's been hung. And the camera lens is going to be that 1 foot below the painting. And then if I draw the line from the bottom of the picture to the camera lens, and this is a right angle here, and I draw the line from the top of the picture to the camera lens, I try to draw the line, I get a couple triangles in here, and what we're being asked to find is the maximum angle that you can subtend by the lens. So the angle subtended by the camera lens is going to be this angle right here, theta. And then I want to notice I have an angle here, alpha, and I have an angle here, beta, and alpha and beta are both associated with right triangles. So I can use right triangle trigonometry to get at them. And theta is just going to be beta minus alpha. And we're trying to identify the distance from the wall we need to place the camera so that theta is maximized, as big as it can possibly be. And what we want to notice here is that we can describe beta and alpha using either the tangent or the cotangent function. So for example, the tangent of beta is equal to, we get 4 plus 1 is 5, the opposite over adjacent. So it'd be 4 plus 1 is 5, 5 over the distance d would be the tangent of beta. And the tangent of alpha, which is this smaller angle here, would be the side opposite, which is 1 foot over the distance d. So this would be 1 over d. We could also describe it using the cotangent function. And remember, the cotangent is just the reciprocal of the tangent function. So instead of 5 over d, you would get d over 5. And here we would get cotangent of alpha. Instead of 1 over d, we would get d over 1, or just d. And so the idea is that either one of these can be used to solve this problem, but the cotangent function is going to be the better choice in this case, because with the variable, the unknown quantity we're trying to solve for, in the numerator position, it's going to make taking derivatives easier to do, and there's going to be a lot less algebra involved if we use the cotangent function as opposed to using the tangent function. So we're going to choose not to use the tangent functions because the variable position in the denominator will make the tangent function more difficult to work with. We're going to say, hey, let's work with the cotangent function. And what we want to do, because we know theta equals beta minus alpha, we want to solve each of these equations for beta. So here I have beta would equal, we would take the inverse cotangent of both sides. So we would take the cotangent inverse of d over 5. And we would take the cotangent inverse, we would get alpha equaling, we take the cotangent inverse of both sides, we get the cotangent inverse of d. And now what we can do is go up here. We see that theta is beta minus alpha, so we can replace beta with the cotangent inverse of d over 5. And then minus alpha can be replaced with the cotangent inverse of d. Cotangent inverse of d. And now I have an equation that relates the variables I'm interested in. The distance I'm trying to maximize, the angle I'm trying to maximize as a function of the distance I want to place the camera from the wall. And because it's a maximization problem, I want to think a little bit about a feasible domain. So clearly the distance, like the worst case scenario would be to be a crazy person and put the camera lens right up against the wall. That would make that distance 0. And there's going to be a back wall over here that's going to identify a maximum distance away you can pull the camera lens. We don't know the width of that room, but that width, we'll call it the width of the room W, is going to be the high end of it. And what we're looking for is critical numbers within this interval. So I'm going to take the derivative, theta prime. I want to find the critical number, so I need to know when is the derivative equal to 0? When does theta prime equal 0? And is it possible for theta prime to be undefined? Because those would be locations of critical numbers to test, and those critical numbers need to live on this interval or they're garbage. So the derivative of the cotangent inverse is just going to be using the formula for the derivative of the arc cotangent function. It's just going to be -1 over, and then it's going to be 1 plus the input to the cotangent inverse function squared. So we're going to get d squared over 25 minus, and then the cotangent inverse of d is just going to be -1 over 1 plus just a d squared. And then I have a mistake here already. So my mistake here on my first derivative, I actually have a function composition. D over 5 is a function inside of the cotangent function. So what I want to notice is that I take the derivative of the cotangent inverse, but then I have to multiply by the derivative of the inside function. And the derivative of d over 5, or 1/5 d, is just going to be a fifth. So I have to do the chain rule here. That function composition requires the use of the chain rule, and I started to get lazy and not do the chain rule in this case. And so if we clean things up just a nibble, I really can write this as a -1/5 in the numerator position, 1 plus d squared over 25 in the denominator, and I have a double negation here, so it looks like I'm going to have a plus 1 over 1 plus d squared. And so right here I've got a complex fraction going on, and it makes it a little bit hard to work with. So one thing that we could do is clean up this complex fraction. And the simplest way to do it would be to multiply by 25 over 25. So if we do that, we would multiply the numerator by 25. So we get -1/5 times 25 is just -5. Over, and then we would distribute the 25 in the denominator into the denominator of the complex fraction. So I'd get 25 times 1 is 25, plus d squared over 25 by 25 will give me just the d squared. And that's why I chose 25. I chose it to kill the denominator on this fraction right here, which then eliminates the complex fraction. And I have plus 1 over 1 plus d squared. And I want to know when this derivative is equal to 0. So the easiest way to do it is to get a common denominator so that we have a single numerator which we can set equal to 0. Because if we can get a single ratio set up, a ratio is equal to 0 only when the numerator of the ratio is equal to 0. So my common denominator is going to be 25 plus d squared times 1 plus d squared. So I would multiply this guy by 1 plus d squared over 1 plus d squared. So we're going to get -5 times the opposite denominator, 1 plus d squared, plus it's going to be 1 times its opposite denominator. So 1 times that's just going to be 25 plus d squared. And then simplify the numerator as much as we can. So -5 times 1 is negative 5, and then negative 5 plus 25 is 20, so we're going to get 20 plus negative 5d squared plus d squared is going to give us negative 4d squared. And this is all over our denominator, 25 plus d squared times 1 plus d squared. And we could factor the numerator, and if I had more space to work with, I would factor the numerator. But because I've got some space constraints going on here, I'm going to go ahead and say, hey, we're doing a maximization problem. It's time to find the critical numbers. Notice the denominators will never be undefined, so I don't have to worry about the derivative not existing. So to find my critical number, I'm just going to set my numerator equal to 0. So I take 20 plus negative 4d squared. I set it equal to 0. I solve for d, so I'm going to get 20 equals 4d squared. Divide both sides by 4. I get 5 equals d squared. I take the square root of both sides, and then usually you would put plus or minus, but remember we're finding a distance, d, and distance by definition is a positive number, so I am not going to put the plus or minus. So we just get that the square root of 5 equals d. So the answer is going to be, but we still have something more to say here. The answer is going to be that we're going to place the camera the square root of 5 feet, because our measurements are in feet. We're going to place the camera the square root of 5 feet away from the wall in order to maximize the viewing angle. The work that we would really need to do extra, because I wasn't able to establish a closed interval, the extra work that would need to be done to justify or guarantee that this was a maximum, because remember, a minimum can also occur at a critical number. So there are two things that we could do, either of which should work in this particular case to guarantee. I'm not going to do it. I'm going to say what needs to be done. I don't have the space to do it. We either need to do the first derivative test, so we need to see if a number to the left and right of the square root of 5, we need to take the first derivative and see if evaluated at numbers to the left and right of the square root of 5 that we get a sign change on the derivative, right? We were trying to show it's a maximum, so we could do the first derivative test, and here at the square root of 5, whatever you get when you plug in the square root of 5 for the angle, we would need to check to make sure that the first derivative switched from having positive slope to negative slope, or we would need to do the second derivative test. So we would need to take the derivative of this guy right here, which wouldn't be fun to do, but wouldn't be that awful. Remember, so the second derivative test would say take the second derivative, plug the square root of 5 into the derivative, and if it's a maximum, if it's a maximum, the graph is going to be concave down, which would mean the second derivative would need to be negative. So we would check, is the second derivative negative when the distance is the square root of 5. If it is, then the graph is concave down, so it corresponds to a maximum. So that's the extra work that would need to be done. Either the first or second derivative test to justify that what we had found was a maximum. If we were being McCheater heads, we could potentially graph this function here and say, oh, by looking at the graph, I can see that it's a local maximum, so I know that the square root of 5 is corresponding to a maximum. That would kind of be the non-calculusy way to justify to yourself that you had a maximum and not a minimum. But that does need to be addressed.